Welcome to G Fun Facts Online. Today we are embarking on a deep time journey, back 4.5 billion years, to solve one of the greatest detective stories in planetary science. We are looking at the Hadean Eon. This is the story of how Earth transformed from a ball of molten rock into the only planet we know of that moves under our feet. We are talking about the origins of plate tectonics. To understand why this matters, you have to realize that Earth is an anomaly. When we look at our neighbors, Venus and Mars, we see dead surfaces. Venus is a stagnant, scorching pressure cooker. Mars is a frozen, thick-crusted desert. But Earth is dynamic. Its surface is a puzzle of shifting plates that recycle the crust, regulate the global temperature, and arguably, make life possible. But it wasn't always this way. Let's go back to the beginning. The Hadean Eon is named after Hades, the Greek underworld, and the name fits. About 4.5 billion years ago, the Earth was not the blue marble we see today. It was born from violence. The solar system was a chaotic shooting gallery. The defining moment of this era was the impact of Theia. This was a protoplanet, roughly the size of Mars, that smashed into the proto-Earth. The energy released in this collision is almost impossible to comprehend. It melted the Earth's mantle down to the core and ejected a massive ring of debris that would eventually coalesce to form our moon. This event effectively hit the reset button on our geology. The Earth became a global magma ocean, a sea of molten silicate rock that was thousands of kilometers deep. As this magma ocean began to cool, physics took over. Heavy elements like iron and nickel sank to the center to form the core, while lighter silicates floated to the top. But here lies the first major controversy in geology. How did that molten surface solidify? And what did it look like? For a long time, the standard textbook theory was that the Hadean Earth was a hellscape for 500 million years. A dehydrated, molten wasteland with a surface that was constantly being melted and remelted. But that view was shattered by the discovery of something tiny. In the Jack Hills of Western Australia, geologists found zircon crystals. Zircons are incredibly durable minerals. They are essentially the time capsules of the geological world. These specific crystals dated back to 4.4 billion years ago. That is mere moments after the Earth formed in geological time. The shocking part wasn't just their age, but their chemistry. When scientists analyzed the oxygen isotopes in these zircons, they found a signature that could only exist if the crystals formed in the presence of liquid water. This changed everything. It implied that the Earth cooled incredibly fast. Within perhaps 150 million years of forming, the magma ocean had frozen over enough to form a solid crust, and the atmosphere had cooled enough for rain to fall and oceans to pool. But having a solid crust and having plate tectonics are two very different things. This brings us to the debate between the stagnant lid and the mobile lid. In planetary science, the default state for a rocky planet is a stagnant lid. This is what we see on Mars and Venus. Imagine a pot of thick soup cooling on a stove. If you let it sit, a thick, hard skin forms on top. That skin doesn't move. The heat below might churn, but the lid stays put until the pressure gets so high that it bursts open in a catastrophic volcanic event. This is likely what the early Earth was like. The mantle was much hotter than it is today. Counterintuitively, a hotter mantle does not mean more plate movement. Hotter rocks produce more melt, leaving behind a dry, stiff residue that makes the crust incredibly strong and rigid. Without water to lubricate the fault lines, that crust locks up. So, if the Earth had a stagnant lid, how did it lose its heat? We can look at Jupiter's moon, Io, for a clue. Io is the most volcanically active body in the solar system. It uses a mechanism called heat pipe tectonics. On a heat pipe world, volcanoes are erupting constantly. The lava flows out, burying the surface under new layers. The weight of this new lava pushes the older, cold crust downward. It is a vertical recycling system, not the horizontal sliding we see with plate tectonics today. A heat pipe Earth would have been a world of thousands of active volcanoes, venting heat directly from the mantle, with the crust thickening and sinking under its own weight. However, the Jack Hill zircons complicate this picture. Some of these ancient crystals contain inclusions of minerals that only form under high pressure, but relatively low temperatures. On modern Earth, there is only one place where you find that combination: subduction zones. These are the places where cold oceanic crust is dragged deep into the hot mantle. This suggests that some form of lateral movement, some form of protoplate tectonics, might have started as early as 4.2 or 4.4 billion years ago. So, how do you start a subduction zone on a stagnant planet? This is the hardest problem in geodynamics. You have to break a solid, cold rock layer and force it to bend and sink. Today, old oceanic plates sink because they are cold and dense. But on a young, hot Earth, the plates might have been too buoyant to sink on their own. We have three main suspects for what ignited the engine. The first mechanism is plume-induced subduction. The Hadean mantle was vigorous. It likely generated massive mantle plumes, mushroom-shaped upwellings of hot rock rising from the core. When a superplume hits the bottom of the lithosphere, it causes the crust to bulge and crack. If the plume is strong enough, it spreads out and pushes the older crust at the edges down into the mantle. Computer models suggest this could create a localized subduction zone. It wouldn't be a global network like we have today, but rather a patchy system of sinking plates triggered by these rising hotspots. The second mechanism is the cosmic hammer. This was the era of the late heavy bombardment. Earth was being pummeled by asteroids. If a massive impactor, say 500 kilometers wide, hit the Earth, it wouldn't just make a crater, it would punch a hole right through the crust and into the mantle. This would instantaneously weaken the lithosphere and create a massive melt pool. The surrounding cold crust, now unstable, could slump into this hole, kickstarting a subduction process. It is possible that the subduction evidence we see in the zircons wasn't continuous, but episodic brief periods of tectonic activity triggered by giant impacts. The third, and perhaps most critical factor, is water. Water is the lubricant of the geological machine. When water enters the crystal lattice of minerals like olivine, it weakens the rock. It lowers the yield strength, making it easier to break. The early formation of oceans meant that the crust was hydrated. As this wet crust was buried, perhaps by the heat pipe volcanism we discussed, it released water into the mantle. This lowered the viscosity of the mantle, making it easier for the crust to slide. This created a feedback loop. Water weakens the rocks, allowing subduction, which carries more water into the mantle, which allows more subduction. This might have been the tipping point that transitioned Earth from a stagnant lid to a mobile lid. Now, I want you to visualize this world. If you stood on the surface of the Hadean Earth, it would look alien. The sky was not blue. There was no free oxygen to scatter the blue light. The atmosphere was dominated by carbon dioxide, nitrogen, and water vapor. The sky was likely a hazy reddish-orange, similar to Titan due to hydrocarbon smog and dust. The oceans were not blue either. They were rich in dissolved iron because there was no oxygen to rust it out. The seas would have appeared green, or perhaps dark purple. And the land? There were no green continents, no trees, no grass. The land consisted of black basaltic volcanic islands and small, gray granitic proto-continents. It was a barren, stark world, constantly reshaped by fire. It was also a noisy world. The constant rumble of volcanoes, the hiss of escaping steam, and the crash of meteorites would have created a cacophony of geological violence. But this violence was creative. The origins of plate tectonics are inextricably linked to the origins of life. We often hear about Darwin's warm little pond, but modern science points toward hydrothermal vents as the cradle of life. Deep in the Hadean oceans, seawater seeped into the fractured crust. It reacted with the hot rocks in a process called serpentinization. This created alkaline fluids rich in hydrogen. When these hot fluids vented back into the cool, acidic, iron-rich ocean, they built porous chimneys. These chimneys were natural electrochemical reactors. They provided the energy gradients needed to drive the first metabolism. But here is the key. Plate tectonics kept these vents active. It provided the fresh rock and the heat. Without the recycling of the crust, the chemical gradients needed for life would have faded away. Furthermore, subduction brings essential nutrients like phosphorus and trace metals from the mantle to the surface. A stagnant lid planet locks these nutrients inside. A mobile lid planet constantly exhumes them, dusting the oceans with the fertilizers of life. It is no coincidence that life emerged on the only planet with active tectonics. As the Hadean Eon gave way to the Archean around 4 billion years ago, the engine stabilized. The mantle cooled just enough, and the lithosphere thickened just enough to become dense and sink on its own. The sporadic, impact-driven tectonics coalesced into a self-sustaining global network. The continents began to grow, floating on the mantle like rafts. This transition marked the end of the hellish Hadean. The carbon-silicate cycle established itself, with plate tectonics acting as a planetary thermostat, preventing the Earth from freezing over or boiling away like its neighbors. This brings us to the conclusion of our story. Why us? Why Earth? Venus was likely too hot. Its water evaporated, leaving a dry crust that couldn't break. Mars was too small. It cooled too fast, and its crust froze in place. Earth was the Goldilocks planet, large enough to keep its heat, but cool enough to have a dense, sinking crust. Wet enough to lubricate the engine, but not so wet that it became a water world with no land. The Hadean was the crucible. It was a violent, chaotic prologue that forged the delicate balance we enjoy today. Every mountain you see, every breath you take, and the very ground beneath your feet is a legacy of that molten genesis. Thanks for listening to G Fun Facts Online.